So in this one, let's just make sure we understand the difference between positive work and negative work. So here's our two scenarios. First of all, what happens if we have, let's say we have, again, our capacitor, our two charged plates. One's negative charged, one's positive charged. And we have a positive charge that's going in this direction. And there are other scenarios we have, again, those same two plates. But this time we have a positive charge going in this direction. So in this first scenario, we consider this a negative potential difference. A negative potential difference. So basically what's happening is that the charge wants to move from the positive to the negative. It's being repelled by the positive, being attracted by the negative. So in this case, it's losing potential energy, but it's gaining kinetic energy. So we can think of this as the field does work on the charge. Okay, so in this case, PE is being converted to kinetic energy. So when we have this scenario, this is when we have a negative potential difference, so negative work. In this other scenario, we have to include applied force. So like in order for us to get from this negative into the positive, we have to go against the field. The charge does not want to go towards the positive, so we have to have an applied force to get that charge away from the negative side. So we're doing work is done on the charge. So in other words, we are supplying potential energy. We are supplying potential energy. So when we have work done against the field, this is what we call a positive potential difference. Okay, so this is positive, the other one's negative. Okay, if we scroll down, so we have a bunch of different equations so far. We have F is equal to KQQ over R squared, so we saw that last day, or might have been 2 days ago, 2 classes ago. And then we have electric field is KQ over R squared. So from this, we can see that electric field is related to force by just taking a force and divided by our charge. So force divided by our charge, we get an electric field. So now we can actually derive in a relationship between electric field and potential difference. So this is the equation we just showed today. Potential energy, that change in potential energy, so that potential difference is equal to Q times electric potential voltage. But the delta change in potential energy is just work. We know work is force times distance. So if we take this equation right here, I'm just going to rewrite it like so right here. We get force is equal to QE, but we also have work, energy is equal to FD. So what we're going to do is we're going to replace force with QE. So you see right there. So energy, change in energy is just equal to QE times D. So charge times electric field times the distance. So we end up with, if we just keep rearranging this equation, we get QV. That's just right here, just doing another substitution right there. Energy, and it's just change in energy is QV, which is equal to QED. Charges cancel out, we're left with V is equal to ED. And this equation is more commonly written as the following. E is equal to V divided by D. So this is for a uniform electric field. So this is only usable in the uniform or the capacitor scenario. So if we have our positive plate and our negative plate, and we have our electric field lines going across, that will be our distance d. And V would be the potential difference. So for example, if we had that 100 volts to 0 volts, that would be our 100 volts would be our V value. D is the distance between those capacitors. And then if we know those two values, we know the electric field. So in this question, we have two parallel plates are charged to a voltage of 50 volts. If the separation between the plates is 0.050 meters, calculate the electric field between them. So again, it's a very straightforward calculation. Let's just draw our scenario again. Our electric field lines go from positive to negative. The direction of positive charge will travel. And we say E is just equal to the potential divided by the distance. Yeah, 50 volts divided by 0.050 meters. And we get a value of 1,000 volts per meter electric field. So I know before we had a different unit for electric field, but this also works, volts per meter. So what that means is in this region right here, inside that uniform electric field, E is equal to around 1,000, or is equal to 1,000 volts per meter. When we get to this outer area though, where it's no longer uniform, we know E is no longer equal to 1,000 volts per meter. It's going to be something less. Same as down here, it's going to be E is less than 1,000 volts per meter. So remember, the density of the field lines determines the field strength. So you can see, if I drew correctly, this distance should be bigger than the distance between these other ones in there.